For today's webinar. We're going to be discussing heat metering standards for the U.S. and have a discussion about the need and potential path forward, in particular for steam metering. Next slide. So today's agenda, let me start by just introducing myself. I'm James Critchfield. I work for the U.S. Environmental Protection Agency here in Washington, D.C. I also, putting on a new hat, I'm also the chair of the ASTM E4425 subcommittee on heat metering. We'll get into a little more details on the background of that subcommittee here shortly. As you can see, we have a series of experts with us today to discuss the issue of heat metering, standardization, and the opportunities that exist potentially in the market on several levels and for several applications. The objective of today's webinar is to get feedback from you on today's topic. We're going to have a question and answer session, as was mentioned just moments ago. We're also going to have the opportunity for you to provide some feedback through a post-webinar survey of sorts. When you click out of the webinar at the end of today's session, a survey opportunity will pop up, and you can put in some feedback regarding today's webinar for us to chew on down the road. Next slide, please. So why heat metering standardization? To put it shortly, it's to assure the accurate attribution of the energy, financial, and environmental benefits generated from thermal energy sources. But this is a broader issue than just steam metering, which today's webinar was titled and focused on. There's also hydronic applications in addition to the non-hydronic applications that we're going to be covering. We will also touch on today's webinar regarding several efforts underway that are being considered and under development for these types of applications. And another benefit of standardization is that we are helping to promote a quality market for heat meter instrumentation. It helps manufacturers meet a single requirement for accuracy, and instead of competing on that level, they can compete on cost and features of their products. Customers also benefit from standardization in that they are able to choose a meter that best fits their needs and their project application, and also it provides them some comfort in that the products that they are selecting are actually performing as indicated or specified. Additional benefits of standardization include assisting policymakers in their ability to implement policies and support markets that are dependent on the accurate measurement or output of thermal energy sources. As we'll talk about in a second here, there's an increasing number of states that are looking at thermal energy, and there is a gap in the market identified through several of these states' experiences that are indicate that standardization would be a useful thing to pursue. And then lastly, to ensure fairness and confidence in the exchange of payments for energy delivery between different parties in the market. A lot of thermal energy is done through contracts and other exchanges of dollars for benefits or energy produced. Next slide. So some of the market drivers, as I mentioned a second ago, a lot of states are starting to look at thermal energy through their state RPS and ERS policies. One of the consequences of this sort of evolution of states recognizing thermal energy is that they are also requiring or have the requirement as they are stewards oftentimes of public monies that are being used for these types of policies, to ensure that what they're incentivizing is actually being produced. Unfortunately, as states on an individual basis look at this recognition of thermal energy through these policies, you're confronted with the possibility of a balkanized environment where each state has their own unique requirement that makes it difficult for manufacturers in the marketplace of instrumentation and also project developers to understand what qualifies from state to state and situation to situation in the market. And so this was identified early in the process as a potential area of risk for manufacturers and other stakeholders as states look at this issue closer. There's also, of course, a trend towards supporting different types of projects, thermal projects, renewable-based projects, through performance-based incentives, that being output-based incentives, as opposed to the traditional and early versions of incentive programs that were more capacity-based or rebate-centric. Additionally, there's a number of thermal energy financial models that are at play in the market that involve different types of purchase contracts that are typically on a output-based basis. So these types of contracts are dependent on the accurate attribution of the energy flows from projects. And also there's just a more broad focus on thermal energy and its use within buildings across the nation, as a lot of stakeholders who have operations are looking at reducing their carbon footprint or their energy use through their building portfolio. It's important that that these individuals and stakeholders can properly assure that they're actually making a meaningful impact. Next slide, please. So I'd like to give a little background on the ASTM E4425 subcommittee on heat metering. In late December, or late 2011 in December, ASTM and IATMO signed a memorandum of understanding to establish a framework for cooperation on the development of a heat metering standard for the U.S. This MOU was a direct result of a proposal that a number of industry players supported and helped drafted. Both ASTM and IATMO are ANSI accredited standards development organizations here in the U.S. and are well prepared and positioned to develop standards of this sort. And these types of standards are voluntary consensus-based standards. In early 2012, last year, ASTM formed E4425 under their E44 Committee on Solar, Geothermal, and Other Alternative Energy Sources. And the E4425 subcommittee is focused specifically on heat metering topics and issues. And there's currently an effort underway under this subcommittee to develop a hydronic application or a heat metering standard for hydronic applications. And that particular standards development is based loosely on existing standards, primarily coming out of Europe with EN 1434 and also OIML R75. For those of you who aren't perhaps versed in the standards development process, you know, a typical question is, how long does it take to develop a standard? Well, the answer, unfortunately, is it depends, because it's largely a function of stakeholder effort. You know, making sure that we have representation from all quarters of the marketplace, from all stakeholder perspectives. It can take anywhere from several months to a few years to develop a standard. I think, if I recall correctly, the average length is somewhere on the order of 18 months. But it can really depend on where you're starting from. If you're just starting from a position of knowledge on the topic already, perhaps there's other standards that exist that touch on issues that are relevant. You sometimes don't have to recreate the wheel, and you can sort of customize the standard for the U.S. market in this case. ASTM E4425 meets about twice a year in person, and we also have virtual meetings through webinars and conference calls, much like we have in today, about every 6 weeks. And so that's sort of a general time commitment if you're interested in following this process more closely. Next slide, please. Just a few words on the ANSI consensus development process. I think the big thing that I would say taking away from this slide is that it's supposed to be a process founded on a broad view of different public perspectives. And so it's, we may be talking about heat instrumentation, and there's certainly lots of instrumentation manufacturers out there that have expertise and the real knowledge of how these types of instruments work, but it really requires a more broad perspective and series of inputs from other stakeholders in the market in order to develop that, what we're calling consensus. And so it's imperative that industries who see a need for such standards of any type, that they provide some sort of feedback through this process so that there's balance, there's consensus, and that there's openness within the process so that the end product is reflective of the industry's needs and is suitable for the application that the standard will serve. Next slide, please. So how to get involved in this process? The ASTM E4425 subcommittee could be viewed as a sandbox for several different standards activities. As I mentioned, we have one for hydronic currently underway. It's early in its development, so there's plenty of opportunity for folks who deal with those types of projects or those applications can certainly get involved. And we're also considering, which is the large part of our discussion today, is a expansion of the standards development activity into the steam application area and non-hydronic applications. Participation can be at any level. You can become an ASTM member, and what that gets you is voting privileges on the actual balloted standards that come out of the process. However, if you are not interested in the membership or the voting opportunities, you can still participate as just a stakeholder in the process, provide input, comment, help draft the standard. All of that is still an open opportunity for you. You do not need to be a member of ASTM. There is an online collaboration area that folks work on standards through. We post documents, have online discussions. There's like a bulletin board, things like that. If you're interested in joining the collaboration area for E4425, please send me an email. Our next subcommittee meeting for E4425 is scheduled for Thursday, January 17th. If you're interested in joining that meeting, I recommend that you contact Christine DeJong with ASTM. She's the staff manager in charge of covering the E44 subcommittees, and she can provide you additional information on getting plugged into some of our upcoming meetings. Certainly you can always email me as well, but there are some registration processes that you need to go through that are not part of the ASTM membership process, but just get you plugged into the actual meetings themselves. So next slide, please. So as we set up today's discussion, we have several experts with us today who are going to go over some important aspects of heat metering in general, but also steam metering in particular, and also some tie-ins to the hydronic side of things. We'd like you as stakeholders and interested parties to start thinking about several questions. Whether you have intention of responding and providing feedback is up to you. As I mentioned, we're going to have a Q&A session that you can ask questions through. There will also be an opportunity in the post-webinar survey, and you can also just email me directly with any thoughts or contact me directly if you'd like to offer up your thoughts on the need for heat metering standards, in particular a steam metering standard, and we'd love to hear about what your relationship to the market and that need is, and what thoughts you have in terms of how to construct or approach the standard itself, what types of concerns you have, those types of things. So with that, I'd like to move to our first speaker of the day. Next slide. Today we have Bowen Ierna, who is Vice President of Onacon Incorporated, which is a Clearwater, Florida-based manufacturer of flow meters and BTU energy meters, specializing in instrumentation designed for distributed thermal energy systems. Bowen is a degreed mechanical engineer from the University of Florida. He has over 20 years of experience in the instrumentation industry and is intimately involved in the design, development, and application of flow and energy measurement systems. We've asked Bowen to join us today to provide a broad overview of steam flow measurement, what's involved with it, what some of the ins and outs of measuring steam is, just to give us a basis for our additional speakers who will be talking more about some of the actual state applications and experiences that we've seen around the country. So with that, Bowen, I'll turn things over to you.
Great. Thanks, James. So as James said, what I'd like to accomplish today is to provide a brief, real high-level overview of steam measurement, and also to provide really a manufacturer's perspective on the need for standardization. As we run through the overview, I'll be pointing out different areas that would benefit from standardization and performance levels. Slide, please. I'd like to begin by reviewing what's happening inside of a typical steam meter. Most steam meters are actually velocity measuring devices, and we know the internal area of the meter, so we can get to volumetric flow rate. The actual density is required to get to mass flow rate, and we'll talk about that in the next slide. And once we get to mass flow rate, thank you. Once we get to mass flow rate, the enthalpy will tell us how much energy is actually in the steam. Slide, please. So getting back to the density side, steam is a compressible fluid, and so density is a function of both temperature and pressure. So there's some additional measurements that need to be made along with the flow measurement. The little caveat there is in saturated steam, temperature and pressure are dependent variables, so you can measure one and still be able to calculate density. And in superheated steam, temperature and pressure are independent, and so you've got to measure both. Again, another little caveat here is in saturated steam systems, you do have to be a little careful. There are areas where you get unintended superheat, typically downstream of PRVs, and if you use a single sensor measurement, that can result in an inaccuracy in the measurement. Slide, please. So now that we've established the measurements required for getting to energy steam, we look at basically you have a volumetric flow meter, a pressure sensor, temperature sensor. Those outputs are brought into a flow computer, and then you're calculating mass flow and getting energy data from the steam flow. Slide, please. Some of the newer technology meters are actually multivariable meters, which have integral velocity, pressure, and temperature measurements inside, and will calculate the mass flow and energy data inside the meter head itself. This gives a couple of benefits. And number one, you can calibrate the meter with all the sensors intact, which results in some improvement in accuracy. Also, you can greatly reduce the overall installed cost of the metering system. So again, that's something to be aware of as we run through this. Slide, please. I'd like to run through here some very important, installation and design considerations for steam flow measurement. These are really in kind of a prioritized order, although that order may change based on application. For example, if you're going into an existing system and you can't shut the steam line down, well, that second to last bullet all of a sudden becomes quite a bit more important and maybe moves up the list. But again, we'll kind of run through these individually quickly here. Slide, please. The first one is being reliability considerations. You have to have a meter out there that's going to work for a good long period of time. And so things to take a look at, are the moving parts in the meter technology? If so, in a steam environment, that will likely require some periodic maintenance. If you're doing waste heat recovery on the water side, for example, you've got to make sure that the water quality is of sufficient quality to be able to have a turbine meter work well over a long period of time. Are there analog transducers that will drift? Can the meter meet the temperature and pressure requirements of a particular application? Are the materials or construction selected properly to prevent corrosion? All those things are going to really factor into the overall reliability of the measurement. Slide, please. Accuracy is obviously another very, very important side of the measurement. The overall steam accuracy is really going to be a function of the combination of the three measurements that we saw we needed to take earlier, along with the calculation uncertainty. One of the tough things, especially for users and engineers, is that overall number is rarely published in manufacturer's literature. And so that's requiring the engineer and user to go out there and do some digging and some calculations in order to make sure that they're getting what they need in terms of overall accuracy. This is obviously an area where some standardization would help tremendously in being able to baseline a certain performance level. Calibration obviously can be very important to the overall accuracy, and there are different levels of calibration. Some meters aren't calibrated at all. Some meters are calibrated electronically. Some meters are put into an actual flow loop and wet calibrated, if you will. And then having calibration certifications with the meter is something that might be very important depending upon what the application is. Also, how the accuracy is expressed is very important. Slide, please. This is a graph that compares a couple of very similar accuracy statements. The red set of lines is a 1% of full-scale accuracy statement, and the set of blue lines is a 1% of rate, or reading accuracy statement. And you can see, out towards the right side there at high flow rates that they're very, very similar in terms of performance. But as you get into more of the typical operating ranges of most systems, you can see there's a very, very big difference in performance of the meter. And this type of statement actually applies to temperature measurement and pressure measurement. And so, again, it's very, very important to make sure that everyone understands the different types of accuracy there. And again, standardization will help that tremendously. Slide, please. Rangeability and turndown are again, another real critical component of meter selection. The rangeability of a meter is just simply the range over which it can measure. So we've got an example here of a meter that measures from roughly 400 to 13,000 pounds per hour. And then you've got some velocity numbers there as well, from 10 to 300 feet per second. Well, turndown is nothing more than the ratio of the high and low limits of the range. So again, in our example, you've got a 30-to-1 range. Slide, please. What's very, very important when talking about turndown is getting back to the actual effective turndown of the meter for the application. So again, continuing our example, we have a meter that has a 30-to-1 turndown from 10 to 300 feet per second. Well, if the application design maximum is 80 feet per second, that meter is only going to have an 8-to-1 turndown for the application. And that might not be enough if you've got widely varying steam flow rates and you want to be able to measure in partial load situations. That kind of leads us into talking about sizing meters properly. Meters should be sized really based on flow as opposed to based on pipe size. And again, with the same example, if we installed a 2-inch meter into that 3-inch application, you more than double your effective turndown, again, which would really enable you to measure a much wider range of flows and be able to measure partial steam loads. Slide, please. Talk a little bit about installation requirements. Most steam meters like to have developed flow entering the meter location. Straight run of pipe is what conditions the flow into that developed flow profile. Note that flow conditioners that can be installed to minimize the amount of straight run requirements, and also that the straight run requirements really are dependent on what type of obstructions are upstream. Slide, please. This is a table of different upstream conditions and really their effects on on the accuracy of metering. On the left, you've got the red dots, which are stay away from. You've got the yellow dots here in the middle, which aren't really as bad in terms of upstream conditions. And the goal here is really to have the flow conditioned to what the meter needs to be able to perform accurately. And that's actually going to vary depending on the actual technology of the meter. And so that's just another variable that's got to be considered when you're making selections. Slide, please. Retrofit installations. This is something that we mentioned earlier. If you've got an existing system and you want to add metering to it, and you can't shut the system down, an insertion style of meter might be something to consider there that can be installed in a hot tap situation without shutting down or interrupting the service. So again, that's just another option. Slide, please. Pressure drop. Here's another thing that that may or may not be important here, depending upon the actual application. This is typically more of an issue in lower pressure systems. Slide, please. So I'd like to kind of close here with a brief overview of some of the more common technologies that we're seeing in steam flow measurement these days. Slide, please. Vortex flow meters have been around for quite a while, and they're very common in steam flow measurement. They come in different configurations. We see an insertion style here, as well as an inline flange style. And you can see a little blow up with a sensor and a bluff body. Slide, please. A common example of vortices, out in nature here is a typical flag behind a flagpole, where you've got wind hitting a flagpole and vortices are shed downstream of the flagpole. This picture on the right is actually a very interesting shot of a volcanic island in the Pacific, and you've got alternating vortices in the clouds downstream or downwind of the volcanic island. Very interesting shot there. Slide, please. Bottom line here is, in a vortex stylometer, that the frequency of the vortices coming off of the obstruction is directly proportional to the velocity of the fluid. And so what that drives to is a meter that is fairly robust. There are no moving parts, and so you get a fairly constant calibration over a long period of time. You do have to watch out, as we mentioned in some of our earlier examples, on sizing, and to make sure you've appropriately selected the correct size of the meter. But again, it's something that's been used quite a bit in steam flow measurement. Slide, please. Another very common class of meters that's used in steam measurement is differential pressure style meters. And as you can see here, there are many different types, from orifice plates and venturis to insertion style to different types of obstructions, as you can see here. There's a little subset maybe of these types of meters, which are variable area meters, where you're actually varying the ID of the meter based on flow rate. Those can be sensed with differential pressure or even strain gauge measurement. But again, there's many different types of differential pressure meters out there that are very commonly used. Slide, please. The differential pressure principle is basically you're putting an obstruction in the flow stream and measuring the pressure upstream and the pressure downstream, and then the flow rate is an actual function of square of that differential pressure measurement. And so again, this is a good, robust technology. It's been used for many, many years. It does have some good benefits. These types of meters, certain versions of them may not be as susceptible to straight runs of pipe. In those types of things. It is fairly difficult to measure a wide range of flows because of the square relationship between differential pressure and flow rate. Slide, please. Turbine flow meters are used to measure steam as well. Again, this is getting back to the reliability side. There are moving parts with this style of meter, and so you do need to be prepared to do some periodic maintenance on these meters, and that'll be a function of steam flow velocities and quality of steam and those types of things. Where a turbometer actually does a good job is in situations, getting back to these retrofit applications, where you can't shut the steam lines down and you want to be able to hot tap an existing meter in, but you can't change the pipe size, so you can't move the velocity. And so a lot of these applications have very low flow steam, and a turbine meter might be a good selection for that type of an installation. Slide, please. And you can see we've got a bunch of conclusions to draw here. But as you can see here, steam energy measurement is a fairly complicated measurement. There are many variables that can affect the performance of the measurement. Steam is a fairly aggressive fluid, so it kind of limits the technology that can be used in the measurement. As a manufacturer, it would be very beneficial to have clearly defined performance levels. It would help in technology comparisons. It helps, when you're in competitive situations, you'd like to be competing on an even playing field, one that's understood by the owner and the user. And as a program manager or user, it can be really difficult to know that an appropriate meter has been selected and also that's installed the correct way to give you the performance that you need in your energy measurements. So again, standardization of these parameters, I think, will greatly help the entire industry. So I think at this point I'm turning it back to James, and we'll go on to the next speaker. Thank you, everybody.
Great. Thank you, Bowen. Thank you for that very good presentation and good overview for us. Just want to remind everybody that if you have a question, you have several options. You can type your question into the question box on the little floating window off to presumably the right of your screen. And we will be answering questions presumably in the order that they're given at the end when we have our Q&A session. You also have the opportunity to raise your hand at that time, and we will try to answer questions from folks directly. And then we will also, if you have any follow-up questions after the webinar, you can also include those perhaps through the survey, and we can try to get some answers for you if possible. So let's move on to our next speaker. Today we have John Ballum. He's a professional engineer with the Massachusetts Department of Energy Resources. We've asked John to provide a bit of a state example for us today of how standardization would be useful in a state situation as it relates to a energy portfolio standard. John is the Department of Energy Resources Technical Resource for Development and Application of Massachusetts Alternative Energy Portfolio Standard for CHP, as well as he oversees the outreach and policy development for the department's CHP program. He has a background of over 30 years in renewable energy, efficiency, and power projects and programs, which included positions as chief engineer with Alton Corp, the nation's first solar thermal and CHP micro-utility. He also has experience as the engineering manager for Luz Construction Incorporated during the design and construction of SEGS 7 and 9 280 megawatt concentrating solar thermal power plants, which have been online since the mid-'80s. So with that, I'll turn over the presentation to you, John.
Thanks, James. Hello. First of all, I'd really like to express the DOER's appreciation for the EPA having taken up the task, much-needed task, of shepherding through a heat metering standard development. So thank you. In my presentation today, I want to briefly cover some of the applications of steam energy, i.e. BTU metering in Massachusetts that I'm either directly involved with or am aware of, and the related need and usefulness for a steam energy meter standard. Next slide, please. So applications for revenue-grade steam BTU meters here in Massachusetts. Currently, we have some state performance-based incentives for steam-generating CHP systems. There is also a fairly extensive commercial district steam heating existing network for the cities of Cambridge and Boston, and there's also the state in the Leading by Example program has begun to monitor and report steam usage for state and municipal facilities for use in analyzing energy usage and efficiency and in meeting energy plan goals, and this is expected to be expanded. Next slide, please. In the future, we'll be adding, where there's a potential that we will be adding performance-based incentives for steam generated by boilers using renewable biofuels and waste heat recovery boilers, and I'll go into that a little more in succeeding slides. Next slide, please. So in Massachusetts, the specific incentives for CHP currently are the Alternate Energy Portfolio Standard, fondly known as the APS, and the Mass Save Efficiency Program. The Mass Save Efficiency Program is an upfront CapEx program incentive, and the metering requirement comes in after the project has been installed and during the monitoring and verification process. So temporary meters are installed to ensure that the performance of the system meets the projected performance. For systems that qualify for the APS meters are accepted by the utilities. Next slide, please. So APS CHP. APS covers other technologies besides CHP, but CHP is the primary generator of credits at this time. So what does the APS CHP program do? It credits CHP attributes of efficiency and net source GHG emission reduction per unit of useful energy generated. Qualified units generate tradable credits based on metered net source fuel energy saved. And the credits then can be sold by the generators to the electricity suppliers so that they can fulfill their obligations under the portfolio standard. Next slide, please. A very simplified, very simplified diagram of a typical a typical CHP plant which is generating steam and requires steam energy meter. So I think the only important thing to see there is that, or maybe counterintuitive, is that you actually typically need 2 meters in order to get your net steam energy. You need a steam output meter and you need a feed water BTU meter so that you can actually come up with the net energy supplied. Next slide, please. Here's an illustration of the obligation schedule. You know, as an example of how a market might be increasing in Massachusetts for steam metering. And this is the obligation in megawatts of CHP that would be required on a yearly basis between now and 2020 to meet the portfolio standard obligation. But just be aware that other technologies could also be generating credits too, and so these would then decrease in terms of CHP. Next slide, please. So a snapshot of the current APS CHP is approximately 65 projects that have been qualified for a total capacity of 65 megawatts with an expected range of net source GHG reduction between 15 and 19% per annum. Next slide, please. The systems with steam generating systems with steam BTU meters, there's 9 of them with a combined capacity of 44.7 megawatts. About 25 steam meters, that's because many of the systems have multiple meters. Range and average capacity of steam generating systems, they range from 2 to 25 megawatts with an average of 5.6 megawatts. Some idea of the range of steam flows and conditions expressed in PSIG, degrees Fahrenheit, and pounds per hour. So you can see the range there, fairly broad. Next slide, please. System types are your standard that you would expect: power boiler plus steam turbine generator, engine plus HRSG, combined cycle, combustion gas turbine HRSG plus SDG. Projected annual revenues for current steam-generating APS systems range between $380,000 to $2.7 million per system. So you can see that as these systems get larger, the revenue impact of the metering becomes increasingly critical. The types of steam BTU or the technologies in place, flow meters, orifice plate, and I really should have called that DP because some of them are not orifice plates, some of them are Venturi, and vortex meters, and we also have one system with an Anubar meter, flow meter. Computers, typically the flow, pressure, and temperature signals either go into an intermediate flow computer or directly into the plant, the existing plant's distributed control system, which then is programmed to be able to compute on a real-time basis and then totalize the net energy, the net steam BTU. Next slide, please. So some idea of how the market for steam may be increasing. We have a rather large potential addition coming along, where there is an existing 255 megawatt merchant CHP plant, which at this time is tied into the city of Cambridge, but underway, under construction at this time, is a tie-in to the Boston district heating system. So this would be an incremental case for the APS, and would create a lot of new credits. And then 3 new steam projects totaling 32.5 megawatts. The DOER, we expect the continued growth in steam generating APS CHP systems, and probably I would say a lot of them in the 7 megawatt in that region, maybe 5 to 7 megawatts. Next slide, please. Potential expansion of the APS. There are studies underway at this time to expand the APS to include systems that would have steam generated by boilers that would be fired with renewable fuels. This would be phase 1, such as biogas, biomass, and biofuels. And then in phase 2, at some future time, waste heat recovery steam generators. An example from a high temperature process stack gas, say at a foundry, with a heat recovery steam generator and possibly even a turbine. Next slide, please. So, given this fairly broad range of applications here in Massachusetts, the DOER does have an interest in a standard for steam BTU meters. In the APS program, even though the steam systems, there aren't that many of them, they are large in comparison with many of the other engine-based systems, and so they represent a large fraction of the program's total thermal energy output, and we expect this to continue to be the case. So because of this, the proper selection and reliability and validity of steam measurements is critical to us in order to meet our program management responsibilities, which the basic ones of which are an accurate allocation of credits and an accurate accounting of source GHG reductions, which is one of the primary underlying motivations for the program. Next slide, please. I should say that we also have a more broader general interest in having accurate steam measurements, in that we work with other agencies in trying to assemble an overall accounting of energy usage and GHG emissions from various sources in Massachusetts, many of which, such as boilers or cogeneration facilities, are metering steam. And so in terms of the quality of that information, a standard would be very helpful. So similar to the ANSI standards for revenue grade KWH meters, a steam BTU meter standard that can be cited by applicants and submittals would greatly simplify the selection, submittal, and review process for both the applicants and us, the DOER, by ensuring that a known level of accuracy will be attained by any meter OEM meeting the standard. Next slide, please. And that brings me to the end of my presentation, and here are some names and contact information for us here that are engaged in this program and these programs at the DOER. Thanks very much. Looking forward to your questions.
Great. Thank you, John. Another great presentation on some of the real-life application of a heat metering standard into a state environment. Let's shift gears a little bit here to our next speaker. We have with us today George Simmons, who's the Director of Intron's Consulting and Analysis Division. We've asked George to join us today and provide us a bit of a perspective on some work that Itron has done with California, particularly with CHP systems. George is here today to share some of these perspectives on the importance of metering accuracy and the value of a heat metering standard to that end. George is responsible for providing utilities, industry, and governmental clients with expert services in the area of renewable and distributed generation, program design, implementation, evaluation, and market assessment. He has over 30 years of experience in the distributed and renewable energy arena, ranging from hands-on development and troubleshooting of renewable energy projects to directing over $90 million in state-of-the-art research and development activities. He has a bachelor's in chemical engineering from UC Davis. And with that, George, I'll turn over the controls to you.
Great. Thanks a lot, James. And good afternoon, everybody. So I'm going to change the perspective, as James mentioned, a little bit here. And you know, Bowen did a great job in describing the nuts and bolts to steam flow metering. John also did a great job in talking about steam metering applications within a program like the APS. And what I want to do today is talk a little bit about how the heat metering data that's collected is used in a program setting where there might be hundreds of CHP systems. And my intent is to really show the value of heat recovery, heat metering, and a heat metering standard. And it's important to understand that while we've talked about accuracy of metering, variability in heat recovery rates is going to be very important in how the results are developed, and then also perceptions about what those results mean. So let's go to the first slide. Okay, so I'm going to focus specifically on California and a program called the Self-Generation Incentive Program. It's been around since 2001. It was originally a peak demand program. It's now really a greenhouse gas emission reduction program. Excuse me. There's more than 530 combined heat and power projects in the Self-Gen program, representing over 240 megawatts of rebated capacity. That's just rebated capacity. The actual installed capacity is greater. And this covers, you know, conventional and renewable fueled IC engines, some fuel cells, gas turbines, and microturbines. Our role in the program has been as a prime evaluator. So we've been installing electricity and heat metering systems. We are responsible for collecting and compiling the performance data and then evaluating the results on both a technology and program performance basis. We've installed over 100 heat metering systems within California. And so you can see the projects are distributed fairly equally over California. And you can also see that IC engines really make up a vast majority of the applications within the Self-Gen program. Next slide. So let's talk a little bit about heat metering within the program. Really, there's three major areas where there's value in heat recovery and in measuring heat. First off, most projects, almost all projects, have to meet some sort of an efficiency requirement. That's true in California as well as elsewhere in the country. In California, there's a public utility code requirement that the sum of the electric generation and half of the useful recovered heat has to exceed a certain percentage of the energy entering the project on an annual basis. In addition, CHP facilities or systems have to exceed greater than 60% system efficiency. Another value of heat recovery, of course, is on obtaining greenhouse gas emission reductions. Again, this is a primary goal of the Self-Gen program, and useful waste heat recovery is key to obtaining net GHG emission reductions. I'll talk a little bit about that later. Lastly, you know, as almost everybody who's attending this webinar understands, that useful waste heat recovery is really critical to the economic viability, not just to the project, but to a project overall, and in ensuring a sustainable CHP industry. Within the Self-Gen program, waste heat's metered by a number of people. It's metered by hosts, by project developers, third parties, and as I mentioned, Itron is directed by the program administrators. We don't have very many steam applications within the Self-Gen program. They're predominantly hydronic applications. And there's a variety of heat metering technologies, including insertion meters, turbine meters, such as Bowen described earlier, as well as ultrasonic type flow meters. It's important to note that, as John talked about for the Massachusetts program, performance-based incentives play a key role, and that's true in California also. Going forward, project developers are going to, well, CHP projects receive performance-based incentives, and the projects are responsible for installing their own metering or obtaining the services of a performance data provider to install electric and heat metering. Next slide. And so you have a variety of folks who are going to be installing these systems. And one of the things that we discovered early on is that sometimes there's confusion about what's meant by useful waste heat recovery. And this seems pretty fundamental, but I just want to point out that, again, you have a host, a variety of folks who are installing these metering systems. And if you look at, you know, a typical generation equipment specification sheet, you're probably going to see that the waste heat out of that generator might be referred to as a useful heat. And there's nothing wrong with that. You know, there's an assumption that that heat's going to be recovered. But that may not be really what you see out in the field. Useful waste heat's really impacted by a number of factors. One of the things that is really critical to understand is that, you know, it's going to be impacted significantly by actual heat demand at the host site. And that can change daily. It can change based on what's happening at the demand within the existing processes, or there can be changes in processes at the host site. So it's important to understand that impact on what you define as useful waste heat recovery. Next slide. So I want to talk about, I mentioned early on that one of the major benefits of heat recovery and heat metering is on efficiencies. We all know that when you get into systems that might have somewhat lower electrical efficiencies, so fuel cells tend to have higher, IC engines, microturbines might have lower electrical efficiencies, then useful waste heat recovery is critical in achieving required efficiencies. One of the things that we've noticed is that when you start talking about a fleet of CHP systems, people tend to look at average performances. But if you're really looking at an average performance, you don't get the whole story. And so if you notice here, the slide on the right is really this 216.6B efficiency, which is the combination of the thermal and electrical. And you can see that gas turbines in this particular instance had a problem achieving that 42.5% efficiency as well as microturbines. And the same sort of an issue with total system efficiency. You know, you can see here that the red part on the right graph, you can see that heat the recovered heat, useful waste heat efficiency is important in terms of overall system efficiency. And again, averages don't tell the whole story. So let's go to the next slide and we'll see what might be happening underneath those system averages. So you get distributions, okay? And so if you look at the slide on the bottom, the graph on the bottom right, we actually looked at what kind of distribution you get in terms of heat recovery rates. And how does that break out? And so these heat recovery rates, these are actually in kBTU per kilowatt hour generated. And so we see that, you know, there's some systems that had really high heat recovery rates, some with very low. Most tended to be banded around 3 kBTU per kilowatt hour generated. If you look up at the graph at the right, what we see here is, you know, this 216.6B efficiency requirement. What's the distribution for microturbines and IC engines? And so again, you know, what we see here is the green bars represent IC engines, the red bars represent microturbines. In this particular instance, you know, the IC engines tended to do fairly well, and there were some that did really well, up there at, you know, 62.5%. So distribution is another way to really understand what's going on with a program and what's happening to your fleet of CHP facilities. That means that although you're collecting data for individual projects, you need to be able to put those into some overall context. And so we tend to use a statistical approach to determine the certainty of the results. And certainty is important because policymakers and administrators tend to look at what's going to happen to this fleet going forward. And so you want to measure your progress relative to current goals, but also what kind of changes do you need to make with respect to the fleet. So again, we look at samples, and we tend to look at 90% confidence and 10% precision, but that's not always the case. And it's important to understand that when you talk about uncertainty, there's uncertainty that's inherent in the measurements, in the heat metering measurements, but also in the distribution. And so when you start talking about these results, you've got to combine those two uncertainties. Next slide. Okay, so what might be some of the factors impacting the accuracy of useful waste heat recovery performance data? And so, you know, as Bowen mentioned early on, you have precision of the metering equipment, and in fact, you know, the in-field precision may not always be what is specified by the manufacturer, just simply because there can be different circumstances than what you'll see under the equipment spec. Placement of sensors is critical. Again, we're talking about useful waste heat recovery and not just the waste heat offset by the generator. So you have to really make sure that you're placing your temperature and flow sensors appropriately, and you take into account any sort of side streams that might impact what you're considering to be useful waste heat recovery. Also take into effect that system configurations change over time, and so what you initially were metering may not be the same if there's a change in the process. Also, metering systems, you know, the performance can change over time. You've got to really maintain systems, and so the bottom right-hand picture here is a new turbine meter on the upper part of that graph or picture versus an older turbine meter. And again, you know, turbine meters, there's nothing wrong with turbine meters. Turbine meters are a great application. You just have to be very careful to maintain them. And as Bowen mentioned earlier, water quality is critical. If you have systems with good water quality maintenance over time, you know, your turbine meter is going to last much longer. Without maintenance, what we've generally seen in California is the turbine meter life tends to peter out after about 3 years. It's also important, sometimes when people are commissioning CHP facilities, they take instantaneous readings, okay? Or they come back and they want to look at what's the useful waste heat recovery at a particular point in time. Well, you know, you might get a very different indication of how the system is performing if you're looking at an instantaneous reading versus you're looking at performance over time. And that also provides you some very important trend information. So it's important to be thinking when you think about a heat metering system, not just the equipment, but also a data acquisition system. And how does that going to be, for a project like the self-gen or the APS, how is that information going to be ported over and what's the time interval? Next slide. So greenhouse gas emission reduction is of more and more interest to folks, and those emissions are influenced by a number of factors for CHP facilities. It's impacted or influenced by electricity that's displaced from the grid by the generator. There's also greenhouse emission reductions due to thermal energy displaced from on-site boilers and chillers from the waste heat recovery system. So you've got to look at the sum of those different things. ANGO just simply refers in this equation here to the electricity displaced both by the generator for the CHP facility as well as the electricity from the grid. And then thermal, the greenhouse gas emissions tied to the thermal end are tied to, again, the heat that's being provided by the generator and being captured and then used in the application. But also, really importantly, is what's that demand, right? How's the heating and the cooling demand at the facility? And what are the efficiencies of the boilers and the chillers? So you have to make sure that you take that into account, because there can be huge variability in what happens with that demand over time. Next slide. So here are some results where we looked at the impact of useful waste heat recovery on net greenhouse gas emissions. And we saw a very strong influence of useful waste heat recovery on greenhouse gas emissions. If you look up at the chart at the upper right hand, again, what we've plotted here is useful waste heat recovery in kBTU per kilowatt hour versus the year. And on the right hand side of the graph, you can see, the net CO2 emission rates. And what we've seen is a steady decrease in CO2 emissions as, in fact, the useful waste heat recovery rate goes up. So the blue bars represent the heat recovery rate. So again, in 2009, 10, and 11, you see a great impact on net GHG emission reductions. The bottom chart really breaks it out between heating and cooling applications within the program. And so what we're seeing in California is that useful waste heat recovery for heating demand at facilities has played a huge role in how you get to net GHG emission reductions. Again, I want to stress that it's important to really make sure when you're putting in projects that you accurately determine what the variability will be in heat demand at the facility. Next slide. So I also mentioned early on that there's an economic value to useful waste heat recovery. And this is huge, because this is what really drives projects and programs, CHP programs forward, is having economic value. And so within California, we've done some economic modeling, both at the program level as well as the project level, to look at what's the economic value. And we look at a number of different factors and actually have some fairly extensive economic analyses that we've done. But we've looked at the costs and the benefits in the self-gen program from different perspectives, from the owner perspective, the utility, ratepayers, and society. And we see that useful waste heat really provides value in different ways. Right immediately to the owners, it's avoided boiler fuel cost. And if you look at this chart here, this is really one snapshot from a model, a fairly comprehensive model. We're looking at 500 kilowatt IC engine that's natural gas fueled. We're looking at the 2015 year within the model. We actually looked at these over the measure life, the entire CHP life, and on a levelized cost basis. So we're looking at 2015, and you can see here with the yellow bar on the benefit to the owner, quite a substantial difference between cost and benefit, on the order of 30% benefit to the owner for that particular year. So you can, again, gain huge benefits to the owner by achieving useful waste heat recovery. We didn't run a utility case in this particular instance, so that's why you see a zero value for the utility. But in terms of ratepayers and society, again, the green bars represent the benefit from those perspectives, and that's really made up of a combination of some reduced gas transportation costs as well as energy costs that are saved from electricity displaced by electric chillers. So again, you can see useful waste heat recovery has substantial economic value. So one of the points I want to make here is that we know that useful waste heat recovery has significant benefits. Good metering is really critical to being able to accurately identify, and then as John had pointed out, you need to allocate those benefits, right? So this is critical on how you allocate them. So accuracy in your results, it's not just dependent on the precision or the accuracy of the metering. That's very critical, but you also have to take into account the variability of the heat recovery rate within the application. And you have to take both of those into account when you begin to talk about the certainty of results. And so good heat metering is critical to achieving that, but most importantly, a heat metering standard is essential. Going forward in a program, a heat metering standard provides everybody with a common approach and a common terminology, and that will help to alleviate any confusion about what the results mean, but also just shed great light on, what are the different components and allocation of those benefits. And so that really concludes the comments that I have about the California perspective on waste heat recovery.
Great. Thank you, George. Another great presentation there. I think now we're going to morph into our question and answer session. Before we get into that, just want to remind everybody that there are two ways that you can ask questions. One would be to submit written questions through the question box on your little floating screen interface, and the other option is to raise your hand, which is also accessible through that same interface using the little tab feature that you see there in the red circle. So right now I believe we have a few questions that have been written into our various presenters, and I will turn it over to a colleague of mine, Charlie Goff, to queue those questions up for each of our speakers, and then we'll move into handling live questions from the floor through the raising your hand option. And one last thing before Charlie takes over is I just wanted to remind everybody that we are looking for feedback from stakeholders on the need and path forward for the development of a steam metering standard here for the U.S. And the questions slide that we had up earlier it'd be useful to get some thoughts from folks either in real time today or perhaps through the survey that will be available for folks as you click out of the webinar today. So there's an opportunity to do that, and you can also email me directly. This is James Critchfield with EPA. So Charlie, the floor is yours.
All right, thanks, James. The first question is for Bowen, and it comes from Gary Fetaplace. I think I'm pronouncing that correctly. But he asks, what impact does steam quality have on the measurement and the reliability of the various meter types?
Okay, thanks. That's a good question. Let me start by defining steam quality. It's basically the amount of moisture that is suspended in a saturated steam environment. It's usually stated as an overall percentage. And the different technologies are going to respond to that obviously differently. Typically, you want to be in the 90% or better range of entrained moisture or that. And the other thing here, the things that are going to affect the steam quality are going to be things like length of distribution, how well the pipes are insulated, those types of things. And so the further away you get and the worse the pipes are insulated, you've got more and more chances of running into problems with steam quality. At some point, the decision needs to be made to put a dryer or a moisture separator into the flow stream prior to the metering, and to make that situation so that you've got a good metering situation.
Okay, thank you, Bowen. The second question came in from Christopher Lindsay, and this is for John. And he asks, what is the current status of CHP in the Massachusetts APS? Is it 65 megawatt electric or 65 megawatt thermal?
Yeah, it's 65 megawatt electric, and our heat recovery efficiency is usually right around 50%.
Great. Okay, and we have another question from Vignesh Gaurashankar, and this is for George. He asks, is the 60% system efficiency for the SGS program based on lower heating value or higher heating value? And George answered that it's higher heating value, but George, is there anything else you'd like to expand on?
Not really. I did mention that the PUC 216.6b is based on lower heating values, so you have to balance those two things when you're talking about self-gen program.
Okay. We have another question from Daniel Humphrey, and I'll leave it. I think this is probably for Bowen, but possibly George, but he asks, for low turn-down steam meters, do you recommend dual transmitters? Or if so, how do you do this with a multi-variable transmitter?
Good question. First, we need to get back to which technology we're talking about. With a dual transmitter, I'm assuming that we're talking about a differential pressure style of meter. I mentioned that a differential pressure meter, the relationship between the measured variable, which is differential pressure, and flow is actually a square function, which limits the amount of turn down that you can have. With the dual transmitters set up, you can actually expand and have two different ranges, butt it up to each other, so to speak, and that's a way of getting much better turn down and low flow capability out of a differential pressure style of meter. So again, that's one way of approaching it. The multivariable aspect of that, I'll have to defer. We are not a manufacturer of differential pressure meters, so I don't know that level of detail. It also gets back into the comments I made about sizing, where whatever the technology is, you definitely want to size the meter to the point where you're getting the maximum capability of the meter that you can. Some of the district steam people will actually use parallel flow meters, and not just dual transmitters, but dual flow meters, and we'll have a high load and low load flow meter, and so they can capture, because on the demand side, you've got to measure from nearly zero flow all the way up to whatever the maximum load is. And so measuring summertime steam usage into a building, for example, it may be difficult to do with any single device, whether it's got dual transmitters or not. And in that case, you might have a 1-inch meter piped in parallel with a 4-inch meter, and valving to go through and select the meter to be used. So good question, though, Daniel. That's a pretty tough application.
So Daniel also asked, why isn't a condensate meter considered?
It can be. A lot of times you don't get all the condensate back. It's trapped out in different parts of the system. And so that part of it is a little tough. We have a lot of customers that measure both the steam output and the condensate, as well as the boiler feed into the boiler, in an effort to see exactly what's going on with the system. And that way you can take a look. You've got, number one, you've got a self-checking instrumentation system, and then number two, you've got the capability of finding out things that are happening in your system that you may not be able to catch otherwise.
Okay, great. We have a question from Charles Collins. I believe this is intended for John, but correct me if I'm wrong, Charles. He asked, for district steam systems that have been operating for many years and have at some point installed renewable energy fuel systems, when might these organizations be able to certify and sell renewable energy credits into the voluntary or compliance REC market?
Well, I'm not sure that I understand the question. So I guess, are we talking about systems which now backfeed into the existing district steam infrastructure?
Charles, if you'd like to raise your hand, we can unmute you so that you can have a conversation and ask your question over the phone.
Charles, are you there?
Hi, Charles.
Okay, I don't think Charles's microphone is working correctly.
Let me proceed on the assumption that I'm understanding it correctly. And as far as I know, that's a very interesting scenario and one which will probably become more and more likely, especially in urban situations where you may have buildings with their own combined heat and power facilities that may want to, much as with the electrical grid, they may want to input steam into the steam grid. And I guess we haven't had that occur yet here in Massachusetts, but I would expect that we would be able to accommodate that in some way into the APS regulations. And if the steam was generated using a renewable fuel, then possibly also into the and generating electricity, then also possibly into the renewable energy credit program. However, I'm sure there would be a lot of details to work out, especially when the steam infrastructure is owned and operated by a private entity.
Sarah, Charles has his hand raised. Should we try one more time to make sure we answer the question appropriately?
Sure. Charles, are you there?
Yes.
Oh, great. Okay.
Can you hear me?
Yes.
I think
Charles.
the last speaker, the last speaker was getting to the point, and that's that, yes, if the system has been producing steam or some kind of thermal energy using a renewable fuel that qualifies in the renewable, definitions of that state or region or whatever, at what point will thermal energy be recognized in the renewable energy credit markets? We have systems that are already in place. We're trying to sell these RECs. We've got active sales that can be made, but it doesn't seem that we can get these certified. And I noticed that Rachel Serrata
Can I ask a question? Is this thermal output from a combined heat and power system or from a thermal system, thermal only system?
Thermal only.
Thermal only.
Steam.
Well, in Massachusetts, as I indicated in my slides, we are studying, and there is a possibility, I think a good possibility, that will be added to the existing APS program, so that steam that is metered, that is generated from renewable fuels, that meets our qualifications, will be able to earn alternative energy credits.
Okay, so Washington State has already done that. They have allowed them for the voluntary markets. We just need to get them certified. And so I guess the question then becomes, what if a state has already done that? Then what's the next step? Should we wait for the steam meter this process to happen, or are we ready to make sales sooner?
Speaking for Massachusetts,
and I'm not sure.
Speaking for Massachusetts, if it should happen that our regulation goes into effect before we have a U.S. steam meter standard, I'm sure that we would proceed as we have in the past with combined heat and power, judging them on a case-by-case basis, or evaluating and approving them on a case-by-case basis. So you would have to work with me if you had a Massachusetts project and submit your proposed metering system, and then I would review it based on our internal requirements for accuracy and appropriateness and survivability and reliability, and then either approve it or not approve it.
Huh. And so the state can certify, in essence, the methodology or the process.
Yeah, that's what we have been doing, but we would like to get out of that business to the extent that we can, which is one reason why we're interested in adding steam metering hopefully to to the development of a U.S. standard.
I don't mean to beleaguer this point here. In Washington State, they've kind of punted, a lot of the utility companies have punted the Green E and Center for Resource Solutions, and so that's the group then that we would have to work with. We're willing to work with them, but potentially it sounds like maybe a state certification process might be a way to go, although we'd be interested in your feedback as to maybe why you want to get out of that business or otherwise, right? Anyway, I don't mean to beleaguer this, but
sure.
I just wanted to raise the question.
I have my contact information, hopefully on the slide there, and I don't know, will these slides be published? I asked the organizer.
Yeah, there's a good chance that we can post the slides from today as well as a discussion online for future use and consumption.
And I think I also may have access to your email address from your registration. So I can send you information on the Massachusetts steam metering requirements and take a look at that.
Thank you.
We have another question from Annie Huang. This is for, I believe, Bowen or George, and she asks, what is the range of costs associated with installing a steam meter at various levels of accuracy and sizes? What are the costs associated with maintaining, demonstrating, and verifying accuracy of the steam meters?
Let me answer that from a manufacturer's perspective first, and then I can turn it over to George or John. The cost of a steam meter in smaller sizes, let's say in the 1.5 to 3 inch size, is typically around $3,000 or $3,500. That's the cost for the equipment only. And then as you get into larger line sizes, the cost goes up because the meter gets bigger. And so, so a 6-inch meter, for example, might be in the neighborhood of about $4,000. So that gives you some idea of where the equipment costs are. From an installation perspective, John, you might have a good handle on this. You've installed quite a few steam meters.
I don't think I have a lot of good information on steam meters, but on meters in general, on full flow meters, full line flow meters, I think we're looking, from a minimum of about $9,000 installed. Of course, up. I mean, if you're going into a 10-inch steam line, you're talking about a lot of money. I think the most important thing is that we have found that in Massachusetts, when you look at the payback, if you are going to qualify for the APS system and earn credits and you have a reasonably efficient CHP system, as you get larger and larger in size, the paybacks on the metering costs get smaller and smaller, to where you're really typically under 2 months for a payback, and given a 10-year lifetime, so you're under, you're at about 2% of your lifetime that you've paid back the metering, and from then on it's paying for itself. I mean, it's making money for you.
Okay, well, we don't have any more questions.
It looks like we have Elizabeth Nixon on the line with her hand raised. Elizabeth, are you there?
Yes, I'm here. I just wanted to mention I'm from New Hampshire, the Public Utilities Commission, and we actually just in December issued a draft regulation for our thermal rec program. And as part of our stakeholder process, we're looking for feedback specifically on the metering as well as other requirements. And like John had mentioned, we would rather not be in this position where we had to look at these on a case-by-case basis, but until a standard is developed, we'll have to do that. But through our regulations, we're trying to standardize that to some degree. So any feedback would be wonderful. And you can go to our website at puc.nh.gov to see that draft regulation.
Okay, great. James, we have a question.
Yep.
I'm sorry, John, were you trying to say something?
That was Bowen. I'm sorry, and I was just answering Elizabeth. I would be happy to take a look and have some suggestions.
Okay, James, I think we have a question from you from Craig Tomsic. He says, will all types of flow meter technologies be considered for the standard or just Vortex, Turbine, and DP?
Well, generally, the approach that we've been taking to date with the hydronic side, and presumably it would be similar on the non-hydronic application side, is we are not necessarily specifying for a particular technology of metering. What we're focusing on is accuracy classifications that any type of metering configuration could apply itself towards. So we're not making decisions or choices, if you will, on what fits into the standard. The standard is really defining the accuracy and the operational conditions that an instrument would have to meet in order to be to fall within certain classifications that are set up. So there are several accuracy levels that meters could apply towards, and then those, if you're tested towards the standard, you could say you're a Class A meter or a Class C meter or what have you.
Hey, James, we don't have any other questions right now, so.
Okay. We are at the 2 o'clock hour, so maybe this is an appropriate time to tie things up. I just want to say thank you to each of our speakers and also for all the discussion from folks who attended today. Just a reminder, in the context of developing a U.S. heat metering standard or steam meter standard, as you click out of the webinar today, you'll have the opportunity to provide some feedback. As you see on the screen, there are some questions to ponder as you perhaps consider providing some feedback. And we'd very much be interested in hearing from anybody out there on this topic. And certainly if you're interested in keeping in the loop going forward, feel free to let us know, and we will let you know of opportunities to engage on the process. So again, thank you for everybody's input, and we'll talk to you next